In this lesson, we're going to evaluate limits at infinity algebraically. So let's review that as x goes to 2, this function goes to infinity. We've seen that with limits, 1 over 0. And so today we're going to, instead of this being a 2, we're going to put the infinity right there. So that's what's different about limits at infinity, whereas x goes to infinity. But look at the connection between this limit expression and also this rational function. And this rational function has a vertical asymptote at 2. So we want to see that when we talk about a limit, it's really just a way to describe the function. The limit is infinity, or when we see the graph is going to infinity, and that's a vertical asymptote. So I guess it's not that new, but today we're officially talking about this. We've mentioned it before. As x goes to infinity, what's happening to the fraction? We can look at 10, 100, 1000 going to infinity. And then what's happening to the value of the function? 1 over 10, 1 over 100, 1 over 1000, and that's going to 0. And we're going to use this. This is our main strategy to evaluate these limits. We have an example, limit as x goes to infinity of x plus 1 over 2x minus 1. When we have this go to infinity and this go to infinity, we get infinity over infinity, and that's another indeterminate form. And here's a way to rewrite it. Let's use the highest degree term of the denominator. So we look at the denominator, degree 1, and we'll just multiply numerator and denominator by 1 over x, because that's the highest degree, x to the 1. So we multiply by 1 over x to the 1, and we get x times 1 over x, 1 times 1 over x, 2x times 1, 2x over x, and then negative 1 over x. But now we just, one more step. We have to simplify everything, and that will be 1 plus 1 over x, 2 minus 1 over x. So these cancel. X divided by x is 1. We're left with a 2. But now we can use this fact that as x goes to infinity, we'd have 1 plus 1 over infinity, 2 minus 1 over infinity. And we saw from this that 1 over x goes to 0 as x goes to infinity. So this is going to be 0, 0, and we'll get the limit of 1/2. So let's just review. Limit as x goes to infinity, 10x. So here there's no algebra to do. As x goes to infinity, we can just look at, just substitute substitute the values, and we get negative 9,286, negative 1 times 10 to the 8th, negative 1 times 10 to the 12th, and those numbers are going to negative infinity. So we see that this function has a limit at infinity of negative infinity. Pause the video and try that one with a table. We're going to negative infinity, so let's put negative 1,000, negative 100, negative 10, and what do we get? Negative 2 times 10 to the 5th, negative 2 times 10 to the 10th, negative 2 times 10 to the 15th. So we see that these numbers are going to negative infinity. So we could say that the limit of the function as x goes to negative infinity is negative infinity. And up here we would say the limit of the function as x goes to positive infinity is negative infinity. And this is the leading term test. Because how could we tell that this is going to negative infinity? We can look at the highest degree, or look at the highest exponent term, highest degree term. This is the leading term test, where we look at this and we know that the graph is going to go in the same direction to the right and the left, and the negative tells us that it's going down to the right, so they're both going down to the left and right. So as we go out to the right, the graph is going down, and that's what we see there. The highest degree, highest exponent is 5. That's an odd exponent with a positive coefficient. So we know the graph is going like this. And then when we look to the left, we expect there to be a limit of negative infinity. But now let's look at indeterminate forms when we have a rational function. So as this goes to as x goes to infinity, we would get negative infinity. As x goes to infinity here, we get positive infinity. So it's indeterminate, and we'll have to rewrite it. So we look for the highest exponent of the denominator, and we're going to divide numerator and denominator by that. Because there's a 2 there, we do this. And that means there will be just write an x squared under each term. So negative 3x squared over x squared, 7 over x squared. So I just copy this and put that under it, copy this and put that under it, copy this. Copy of 1, put x squared under it. Then we can reduce. So cancel, and we get negative 3. Nothing to cancel there. Cancel, and we get a 5. Nothing to cancel there. All right, so we're going to have negative 3 stays that way. 5 stays that way. But when x goes to infinity, we have 7 over infinity, which is 0, plus 0, and another 0 there. So then we have the limit is negative 3/5. Pause the video and try that one. If we put infinity there and there, we have infinity over infinity, so it is indeterminate. That means we need to rewrite it. So we look for the highest degree term of the denominator. Let's divide everything by that. So 4x, copy 4x and put it over x. Copy 5 and put it over x. Copy 8x and put it over x. And reduce. Cancel, we get a 4. 5 over x. Cancel, we get an 8. 3 over x. As x goes to infinity, this goes to 0, so we get 4 over 8, or 1 over 2. Okay, pause the video and try that one. Putting infinity there and infinity there gives us infinity over infinity, indeterminate, so we have to rewrite it. Let's use the highest degree of the denominator. We could use the highest degree of the numerator. It won't matter. Let's just go ahead and do this, since we've been doing that. So we copied everything and put x cubed under it. And now we're going to reduce it. So we get 6 over x minus 1 over x squared. This x squared cancels with 2 of these, and we're left with 1x. Here the x's reduce, and we'll get 1 over x squared. Here the x's divide to get 1. And that stays. So that's going to be 0 minus 0 over 3 minus 0. And that equals 0. So remember that we don't have to divide all the terms by, here we wouldn't have to divide by 1 over x, or divide by x, because we can do direct substitution and it's not indeterminate. So we have, that's 5 over negative infinity. That's okay, it's not indeterminate, and we know it equals 0. All right, pause the video and try that one. So if we put infinity in, we get infinity over infinity, and that's indeterminate. So we should rewrite it. Let's look for the highest degree of the denominator. Or the degree of the denominator. So we'll copy everything, put an x under it. So that reduces to negative 3x. This reduces to 5 plus 1 over x. And what's happening as x goes to infinity, that'll be 0, 0, 5, but that's negative infinity over 5. So the limit as we go to infinity is negative infinity. And let's just go back and review piecewise functions. And if we want to limit it to, we have to look at the limit as x goes to 2 from the right, the limit as x goes to 2 from the left, and then that will tell us what the limit as x goes to 2 from both sides is. And here it's just looking at, okay, we're to the right of 2, that means we're using this function. So we're going to do 2 minus 6. Because if it says go from the right, this means from the right. We're going to the right of 2. So we're going to use that function, and we substituted 2, negative 4. Go from the left of 2. This is the left of 2. So we use that function and substituted 2. 0 plus 1 is 1. And we can say that this does not exist because it has different limits from each side. And pause the video, try that one. So we're going to 0 from the left. That means we need to use this piece, and we substituted 0. 0 squared minus 1 is negative 1. Let's go to 0 from the right. That means we're using this piece. Plug in a 0. 3 times 0 plus 1 is 1. Since we're not going, since the one-sided limits are not equal, then the limit as x goes to 0 does not exist. We'll stop there.